Hello, everyone, and welcome to the Quantum Webinar Series featuring Dr. Bill Wisotsky on the topic of applied quantum AI in the NISQ era to address real-world problems. I'm Farouk Garamani, Vice President for Research, Innovation, and Sponsored Programs at New Jersey Edge, and one of the moderators for this event. The Quantum Webinar Series is a partnership between the Ecosystem for Research Networking, ERN, and the Northeast Big Data Innovation Hub that brings together leading researchers, students, industry experts, and innovators to explore the latest breakthroughs in quantum science and technology. Next, please. Well, we want to draw your attention to the Code of Conduct for the Northeast Big Data Innovation Hub. The Northeast Big Data Innovation Hub promotes a safe environment free from any type of discrimination or harassment, and participants are expected to abide by the principles that are listed in the Code of Conduct, which is posted in the chat area. Our moderators for today, including myself, is Florence Hudson, who is Executive Director of the Northeast Big Data Innovation Hub, as well as the founder of the National Student Data Corps, as part of the Data Science Institute at Columbia University. And Florence is also an ERN steering committee member. Emily Rothenberg, who is the program manager of the National Student Data Corps of the Northeast Big Data Innovation Hub, Data Science Institute at Columbia University. And it is my pleasure to introduce Bill Wisotsky, Principal Quantum Systems Architect for Research and Development at SAS. Bill began his academic career at SUNY Albany and later pursued a PhD in behavioral neuroscience at CUNY, where research on neural pathways and photon absorption sparked his interest in quantum. Since joining SAS in 2002, he has continued advancing the expertise in quantum technologies through seminars and hands-on experimentation, helping to launch the Applied Quantum AI Initiative at SAS. Bill, in his current role, leads efforts to integrate quantum computing into real-world business solutions. Welcome, Bill.
Thank you. I'm just going to share my screen here. Okay. You can see it, right?
Yes.
Excellent. Okay, my name is Bill Wisotsky. I'm the principal quantum systems architect at SAS. Thank you so much for the introduction. Um, Before we get started, I want to talk a little bit about SAS for those of you that may not have heard of SAS before. But SAS is 50 years old this year, and over the last 5 decades, organizations have counted on SAS in times that mattered most. We did a lot of statistical analysis work during COVID with many of the universities and pharmaceuticals. SAS ranks as a leader in 47 different evaluations, including artificial intelligence, machine learning, and data science across virtually every industry. But there's more important than those statistics are the values that SAS has. So part of our value statement is our vision, which is to be the most trustworthy data and AI partner that powers the world's decisions. And secondary to that is our mission, and that is to provide knowledge in the moments that matter. And these values are important when it comes to quantum because we strive to be the trusted advisor or the voice of reason when it comes to quantum computing. We're not a quantum computing company, and we will use quantum computing or quantum AI when it makes sense or when it adds value to our customers. If it doesn't add value, we'll solve the problem classically. So, what is quantum computing? And I get this a lot, and I use this as an example all the time. And I like to use this. Can you see my mouse moving around? Um, I like to use this mountain range example. And let's say ask you to take a look at this lake at the bottom of the mountain range, uh, and I want you to find this lake. And I'd only give you a compass, and you could start searching through this mountain range, and you might find this lake just by chance the first time, or if you take a look at the vastness of this mountain range, you could pretty much spend your entire life doing it. This is almost like a two-dimensional search space, right? You could go left and right, you go forward and backward, and you have to follow the terrain of the mountain. You can't really get to a higher dimension to look for this lake. If I was to ask you to use a quantum system or like, a quantum method to find it, it would be equivalent to you getting into a helicopter, projecting yourself into a higher dimension and being able to fly around the mountain range and see every possible solution, every possible path, every possible location all at the exact same time and choose the best one and find the lake. So this is an analogy that I like to use because it's very, very clear. When we talk about quantum computing, I guess the question is, why do we really care about it? We care about it for a lot of reasons. One is purely money, right? I mean, this is from McKinsey and Company. It's a 2024 report. The 2025 just came out this week, which I haven't had time to incorporate. But if we take a look at this, we're talking about market size or market value, right? And this market value is not quantum computing companies. It's every single organization and company that has some sort of involvement with quantum computing. It could be end users, it could be customers, it could be financial services, anything that touches quantum computing. And they have it divided into different categories: quantum sensors, quantum communications, quantum computing, communications, and quantum sensors. The important thing to see here by 2035, they're projecting between $1 and $2 trillion in total economic value, and this has increased steadily over time. So there's a lot of money at stake in quantum computing. If we take a look at this chart, this is one of my favorite charts. It shows 2025 to 2030, and then 2030 to 2035. And what these boxes here mean is the legend here shows low economic value, medium, and high. If we take a look at this broken down by industry, you can see that from 2025 to 2030, financial services, chemicals, and pharmaceuticals are really the ones that are gaining medium economic value from quantum computing, with everybody else in the low. But it's projected from 2030 to 2035 that actually changes, right? So now the only one that's actually getting low economic value is media and entertainment. Everything else is medium to high, which means there's going to be more money and more jobs. And if we continue looking at the jobs, if we look at the labor market, and this was published by MIT, if we from 2010 to 2024, job postings that require quantum skills, you can see it's a steady increase over time. So if you're in school now, it's a perfect time for you to learn about quantum computing because the market is just beginning. So what is quantum computing? What makes it special? Well, the first thing I want to discuss is something called the block sphere. And the block sphere is how this is not what the quantum computer looks like, right? It's a visual aid that we use to visualize something called a qubit, which is analogous to a classical bit, but it's a quantum bit. Now, the important thing here is like a classical bit, you have a 0 and 1. Quantum bit, you have 0 and 1 too, but you also have two other dimensions that you can represent data. You can represent data on this Z basis or the north-south pole. You can represent it on the X basis, right, or the Hadamard basis, which would be equivalent to a superpositional basis, or a Y basis in imaginary space. So right off the bat, you could see that now you could represent your data in a three-dimensional plane and any value around this block sphere. So right off the bat, the representation of data is more powerful. So what does that mean from using classical bits versus qubits? Well, you can think of a classical bit, as I mentioned before, 0 and 1, like a light switch. You turn it on, you turn it off. There's no in between. It's either 0 or 1. Well, we already discussed what a block sphere was. Here's another visualization of the y-axis, x-axis, and the z-axis, y-axis, and x-axis. But you could see that it doesn't have to be a 0 and 1. It could be anywhere in between 0 and 1. It's like a dimmer switch for a light, right? It doesn't have to be 0 or 1. It doesn't have to be on or off. It could be some intermediary in between, which is dictated by the probability of finding it between 0 and 1. And these probabilities are alpha and beta in this quantum state psi. And this is what a superposition looks like. So what exactly does this mean? Well, you can think of a coin. If you're spinning a coin, it's neither heads nor tails while it's spinning, but when you slap that coin down, you collapse that state into either heads or tails. But until that you collapse that state, you have access to both heads and tails at the same time, but it's neither one. Now, if it's a fair coin, you would expect alpha and beta for heads and tails to be 50-50. If it's an unfair coin, it's going to collapse to whatever that probability distribution is. The same thing what happens with qubits. So why is this powerful? Well, if you think about having one qubit, you have, for example, the coin, you have access to two simultaneous quantum states, both one and zero, at the same time until you collapse and make a measurement. If you have two qubits, you have access to four states, 3, 8. This increases in exponential way from 2 to the number of qubits. Another way of thinking it is if you have one qubit, is equivalent to 2 bits, 2 qubits, 4 bits. And if you extrapolate that out, when you get to 300 qubits, you have theoretically a larger state space than the number of atoms in the observable universe. So until you make a measurement, you have access to all these different states that you could do computations on. Similar to that helicopter flying above the mountain range, you have access to the entire solution space. Another quantum physical property that we use in quantum computing is entanglement. And some people will talk about entanglement being similar to a correlation, but a correlation just means that they vary together. In quantum entanglement, they become entangled where, in a sense, you can't discuss one without the other because they are completely dependent on each other. It's more than a correlation. And a good example that Professor John Preskill talks about is a book. And he compares a quantum book versus a classical book, where a classical book, the pages are not entangled with each other. So you could read a page in the book and derive meaning from that page by itself. The information is encoded into each page separately in the book. A quantum book where the pages are entangled, you can't make any sense of one page versus the other. So you could read a page and you'll derive absolutely no meaning. It would just be random words. The only meaning is encoded in the entanglement of all the pages in the entire book. So that's how entanglement works. And we see spooky action at a distance because it's also distance independent, right? So in theory, you could have two particles separated at opposite ends of the universe. And when you observe one, you know what the other one is. It's kind of like you have a left and right shoe, and you put a left shoe in a box and a right shoe in a box. You ship one off to the opposite end of the universe. You open up your your box. You find that you have the left shoe. You know that wherever this other one is, that's going to be the right one. So how does this all work? Well, on the left-hand side, we have sort of a classical maze. You can think of every left-right decision as a 0 and 1 possibility. You have to check left, you have to check right. Is that the right way to go? No, you have to check every single, left-right combination till you get to the end of the maze. In a quantum maze, using superposition and entanglement, you could explore every left-right combination at the same time. And through sort of a constructive and destructive interference, you wind up subtracting out all the incorrect answers or all the incorrect paths and only keeping the correct one. So when we talk about quantum machine learning, which is our next topic, we need to talk about the types of the strategies. So on the left-hand side, we have the type of data, classical data or quantum data. On the top, we have classical machine learning or quantum machine learning. So in this first box is classical machine learning on classical data. That's what we're all, we spent years doing, right? Standard linear regressions, random forests, just on classical data sets. This one is classical machine learning on quantum data. So, but what exactly does that mean? Well, an example would be using quantum sensors to generate quantum data that you feed into classical neural networks or classical AI. That would be an example of this. And we're going to talk about some of that a little bit later. And then we have quantum machine learning on classical data. That's what people think about when they think about quantum machine learning. You have this classical data set and you run quantum machine learning on that classical data set. And then finally, we have quantum machine learning on quantum data, where you have, let's say, quantum sensors that never collapse their data into classical states, that they automatically transfers that state vector, or however you're measuring it, or however you're recording it, into quantum machine learning algorithms. And these are important because they are all used somewhat differently. We're going to talk about a couple of different examples. So before we go down these examples, I want to talk about algorithms. Now, there's a reason why this picture's on the screen. It's a framing of a house. And let's say I tell you, I ask you, I want you to build a house, but I'm only going to give you a hammer, tape measure, nails, and a saw. Well, if you're really, really skilled, you might be able to build a house just with those four tools. But most likely that house is going to take a very, very long time to build, and everything is probably going to be crooked and not sturdy. These tools are what are algorithms are the tools that allow us to do useful things with quantum computers. So without algorithms, quantum computers really don't do much. Um, and it's important to understand that when we talk about algorithms, on the left-hand side of this was a quick search that I did. It's not exhaustive, but it gets the point across. These are all the classical machine learning algorithms that exist in this sampling that I did. And on the right are the quantum machine learning algorithms, similar sort of search. Now you can see right off the bat that there's a vastly different amount between the two. But if you take a look at the check marks, these green check marks, those are the ones that can run on current noisy intermediate scale quantum devices, the quantum computers that are around today. So you can see that that's even a smaller subset. But when you take a look even further and you look at the QRC, which stands for quantum reservoir computing, we have it for gate, analog, and spin. And then we have another one down here. So are those really four different algorithms, or is it really just one algorithm, which is notated over here, just on different modalities? So we can continue breaking these down. So we wind up with about 10 different quantum algorithms that are highly used for quantum machine learning. That's equivalent to me asking you to build the chat GPT and only giving you the tools of a t-test, ANOVA, and linear regression. So my point being here is that for quantum computers to be useful, we need to have the tools to make them useful, and those are the algorithms. So there's a lot of research being done in algorithms, and if this is a field that you want to go into, there's plenty of jobs out there for algorithm development. I'm going to talk about two major types of algorithms. One is called the variational approach, and I'll explain why we call it a variational approach once I'm finished with the slide. The way this works is you have your classical data set, right? This is a classical data set and using quantum machine learning. This is that example. Your quantum computer is automatically initiated to every qubit to a state of zero. In this stage, you have to understand that quantum computers do not understand what classical data is. We have to take our classical data and encode it into a format that quantum computers understand. There's a variety of ways of doing it, and which way you do it does affect your results. There's angle encoding, where you take your data, you normalize it, and then you create angles in radians, and then you project that onto one of the axes of the block sphere. You have amplitude encoding, you have bit stream encoding, and then you have a whole bunch of other ones. Um, Once the data is encoded, then you run it through your quantum computer, and these are called an ansatz. It's a collection of parameterized gates. The parameters are thetas, so rotation on the z-axis, rotation on the x-axis, on the y-axis, and these represent entanglements. Now, it's really important to understand that the next stage is your measurement stage, and we have this word shots here, and that's because quantum is not deterministic; it's probabilistic. And because it's probabilistic, you can't just run this once because the results don't mean anything. You have to run it thousands of times to get a probability distribution of answers, and the answers that come out as the highest frequency are most likely the right ones if you design this correctly. Now, if you take a look at this, this looks very, very similar to a standard feed-forward neural network. You have your input nodes, you have your output nodes, and then you have your hidden nodes in the middle. And instead of a weighting function for the nodes, we have this theta. And this theta is the angle or the degree of rotation around the z-axis. And this is what's being varied in this variational approach. What happens after we measure, we compare them with our predictions or our labels, and then on a classical computer, we run an optimization routine that optimizes the thetas to minimize a loss. And then we feed these thetas back in, very, very similar to a feed-forward neural network. We feed these thetas back into the ansatz or the quantum computer, and then we run it again, and we run it again, and we run it again until we converge at a minimal loss, and that would be our configuration of our variational approach. The reason why it's variational is it varies between quantum and classical, quantum and classical. It's a hybrid approach. Everything in quantum computing today is hybrid. And this is actually a diagram of a quantum neural network. This is one algorithm. Another type of algorithm, and this is what we're doing a lot of research on at SAS, is what we call the quantum reservoir. And you'll notice some major differences. One major difference that is going to be pointing out right, I'm going to point out right here is there's no variational step here, right? There's no back and forth between quantum and classical. When you do that back and forth between quantum and classical with that optimizer, you run the risk of things like barren plateaus and vanishing gradients. So there's problems with variational approaches. They can be controlled to some extent, but they exist. This doesn't have that problem. It might have other ones, but it doesn't have that one. The steps are the same, your classical data, your encoding, but in this case, you have a reservoir. And you'll see that it's a very, very different diagram because what the reservoir is, it's a quantum dynamical system that's set up through the use of sort of random rotations and different types of entanglements. You could do an entanglement using a controlled Z gate or a controlled X gate or controlled Y gate. You could do multi-qubit gates. You could also, this reservoir doesn't have to be in a digital quantum computer like the circuits I'm showing you. It could be an analog quantum computer like using Quera, where you're evolving a Hamiltonian over time and you're controlling the neutral atoms, the properties of the neutral atoms. So this will work in an analog format as well. And then you make your measurements. So you make your measurements once, not you still have the shots, right? You're still measuring thousands of times, but you're not going back and forth between quantum and classical. But if you notice here, that training procedure that we were talking about before is not happening. We're running the system through once, and then we have this blue box over here. And this is one of my favorite algorithms because it allows us to take our output data set. And you can imagine that the way the reservoir works is that, remember when we mentioned that we have two to the number of qubits, right, of possible outcomes. If we have our, let's say, 4 qubits here, we have 2 to the fourth power columns that get transformed out of this. And that could be, and they're represented as bit strings. You can imagine when you measure this, it could be 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, and so on and so forth. Each possible combination that this could exist in gets output as a column in our output data set with a probability of getting that bit string for that row of data. So you can see we're constructing a data set that is almost like a higher dimensional representation of our original data set. This new data set is used as the training, test, and validation data sets into any one of your number of classical machine learning algorithms, logistic regressions, deep learning, neural networks, whatever you might want to use, decision trees, and that's where all of your modeling is happening. So in a way, you can think of this as a quantum data transformer. It comes in as one format, it gets transformed and projected into a higher dimensional Hilbert space, and then read out, and then that's your data set going into your classical models. From a SAS perspective, this works really well because we have our data set. We could run our data transformer from SAS code or from data management or from our model studio, and then use the breadth of our classical algorithms against that data set. So quantum reservoir computing is similar to classical reservoir computing, right? So the question is, what exactly is the difference? Because classical reservoir computing does something very similar, but what it's doing differently here is it's using quantum physical properties to create these higher dimensions. We're creating these like we mentioned before, we have these three-dimensional representations. We have the quantum entanglements, we have the superpositions, and we have our constructive and destructive interference effects. Those are what goes into the reservoir and constructs the dynamics of your reservoir. And what comes out is a sort of higher dimensional representation of your data that is based on the output and the effects of all of those different quantum physical properties. So when we talk about these things, we talk about applied quantum computing, and that's what we're really focused on at SAS. But before I talk about, use cases and things that we're doing, I want to kind of set the stage a little bit. This is the computer that I first learned on back in the late 1970s. It was a Commodore PET computer with a whopping 7,000 bytes free. And there was this tape deck that was here. And you would put your tape in the tape deck and you would type on this sort of keyboard, load in the program name, and you would wait a half an hour. And it would load it from a cassette tape. And then you would type run in the program name, and then you would all get immediately syntax error line 14. and you would load it again and do the same process, and then you get syntax error line 18. And then you do it like 3 or 4 times, and finally you would get a clean load of this. And why did it happen? Because you're reading a magnetic tape, so there's going to be errors in that transfer of data. So finally you get this program that runs, and the entire time you're saying to yourself, what is the use case for this, right? This is like cool, but like really, I just had to load this thing 4 times. I took an hour to load this. Um, And that brings me to my next example. And I'm going to come back to all of this. Here's one of the first cell phones. I remember, when I was a kid, some of the richer kids that I grew up with, their parents had these, and it was a suitcase. You actually wore it on your shoulder, and when the phone rang, you pulled this headset out of this suitcase cell phone. And again, you're like, all right, this is kind of cool, but now, you're walking around with a suitcase all day long. Is it really practical? And then here we have a rotary phone. This is the phone that I grew up with. And here was a modem. If you saw the movie War Games, you would dial another computer and then you would listen to that, the crazy tone that you would hear, and then you would put it on the receiver on this modem, and then you would tie up your phone line for the next hour because you didn't have call waiting at the time until your mom would scream at you from the kitchen to get off the phone. And all of this was just textual, right? You just were on bulletin boards just sending messages. For each one of these, the question is, where's the future of this? At that time, we never would have thought that we would have computers that we have today, um, compared to this pet computer. We would never think that we would have iPhones or 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 high-speed data that I'm streaming videos and TV into my house. But the one thing that's important to remember is that all of these transformed the entire world as we know it. And we have the benefit of hindsight today. So we see the quantum computers. We see what they might be capable of through this hindsight of just using our imagination. But whatever predictions we make today, I am convinced that if you ask me to make a prediction today, um, in 5 or 6 years, my prediction will be grossly understated, right? Things are going to be very, very different once we get fault-tolerant quantum computers. So this is where we are today. This is the hardware that we're working with today, equivalent to what this was back in the 1970s for classical computers. So, since I set the stage of where we are today in quantum computers, it's amazing that we're able to see any sort of quantum utility, right? Compared to classical computers. The fact that we're able to see some level of quantum utility with the minimum number of qubits that we have, the non-error corrected qubits, so on and so forth, is a great thing. So, we've done a bunch of different research projects. We've done work in the insurance industry with disaster response. We've done a bunch of projects in financial services around fraud, bankruptcy, collateral optimization. And all of these are applied quantum projects. They're not toy problems. They're not working on the MNIST data set or the IRIS data set. These are real data sets that have come to us from customers. We've worked on POCs in healthcare. One of them I'm going to talk about today, uh, as well as manufacturing in factory optimization and mixing of I'm actually going to talk about that later in consumer packaged goods. And finally, we're also experimenting with digital twins. So we have a relationship with Epic Games to use the Unreal Engine to create digital twins. In some cases, right, you might create an optimization uh, solution for a factory that can't afford to change their current optimization solution because if it doesn't work properly, then they're going to be behind the eight ball in getting things out to customers. So we create a digital twin and we implement the new optimization algorithm in the digital twin. We run it fast in a digital twin compared to the regular twin, and we see what the results are. So it's our sort of sandbox that we could start playing with. Um, as far as use cases, I believe 3 use cases, and these are real world use cases. The first one I'm going to talk about was for fraud and bankruptcy in financial services. The first thing I want to discuss is if you think about quantum machine learning, it adheres to the same rules as classical machine learning. So it's very much a hybrid process. You have your pre-processing that you have to do, right? You have to take your data, you have to do your data management, you have to explore the data, see what the relationships, you have to establish classical baselines. So anytime we get a problem from a customer, remember, we're not a quantum computing company. We're trying to find value for the customer. We're going to get our best experts classically to see if they can't build a good model. And then we look at quantum, and if we could beat those models or add to those models in some way, then we will use quantum. If we can't, then we won't. A good example is we were working with an insurance company for a disaster response, and they were having problems with their optimization algorithm, and we thought it could be quantum. We put our best experts on it, and they reformulated the problem. I mean, we're talking experts that have been doing this for over 20 some odd years. And they reformulated the problem. We were able to solve it in a minute and 30 seconds. So there was no point in using quantum. In other cases, we see that there's certain areas of a problem that are very computational expensive or not expressive enough, and then we'll start introducing quantum. So we establish baselines, we do our post-processing, and um, just because you follow the same rules doesn't mean that the same things hold, right? You still have to do the pre-processing, the data exploration. But like, for example, in classical machine learning, if you have collinearity amongst your variables, that's not a very good thing. You want to get rid of that. Well, that's not such a bad thing for quantum because in quantum, you could entangle the correlated variables and allow the quantum entanglements to explore those correlations in ways that we simply can't do classically. So, because you're following the same procedure doesn't mean the rules governing those procedures are exactly the same. But it's a hybrid process. And in this case, what we did is we used the quantum reservoir computing algorithm that I showed you before. So here we have our data access, our data integration, all of our data steps. We create our data set from multiple sources. We do our sort of initial data mining, our reporting, our filtering, our validation, and we're still in the data phase, right? We're still trying to figure out and make sense of all this different data set. Once we do that, we do our quantum encoding into the quantum space. We run it on a quantum computer. In this case, it was the quantum reservoir algorithm that we showed before, and then we get our output data set. And this output data set is then run through all of our model studio algorithms such as linear regressions, logistic regressions, neural networks, decision trees, and then we pick out the best model from that. All of this is happening within SAS. The only pieces that are not are the pieces that need to happen in a quantum computer. So, as I mentioned, it's truly a hybrid process where we have the quantum computer doing what it does best. In this case, these higher dimensional projections. Here are some preliminary results of this. This is an ongoing study that we're doing. But if we take a look, what we have here is we have accuracy AUC, the F1 score, the precision recall AUC, precision for the event, and recall for the event. And we found that you can't just look at AUC. You have to look at everything to get a holistic view. We have three different bars here. The blue is the classical data set that we would just take classically and then do some sort of, clean the data and run it through a logistic regression, a ridge regression, or support vector machine. In this case, those are the ones that we used. We have our combined data set and our quantum data set. The quantum is the quantum projections. That was what we discussed earlier in the QRC. We ran those through the same exact algorithms, the classical algorithms. And then we have this combined data set, which I did not mention before. The combined data set is basically the classical data set augmented or combined with the quantum data set. So it's basically a horizontal merging of the data together. And if we take a look at this, the combined data set typically does better than either one does by themselves. There is some variability between the models, but that's to be expected, right? If you have a classical data set, you put it into our Model Studio product and you put 10 different models on it. Some are going to do really well, some are not going to do really well. And that's the whole point that's the whole exercise of modeling to get your champion model. So that doesn't surprise me. But we see this pattern emerge that this combined data set typically does very, very well. In some cases, classical does better in this example here. But overall, this is what we are noticing in this financial data set. The other thing that I did not mention is that we're able to build a very similar model in prediction, or in some cases better than a classical model with far less data. Quantum computers need far less data to build models than classical computers. And that's because of this idea of superposition and entanglement and the ability to explore this data in such a higher dimensional space.
Bill, there's a question in the chat.
Sure.
Are you okay with taking questions as we go, or would you prefer to wait till the end?
It doesn't matter to me.
Oh, so the question is, are you familiar with JP Morgan's paper on required qubit counts and error threshold for a lower bound on quantum advantage? Have you found similar results in other use cases? Approximately 73 million qubits needed.
I haven't read that paper.
Okay, thank you.
And here is another example. And this is one of the first POCs we did. This is an optimization example. And this is a really good one because it really hits home for a lot of people because it's a kidney exchange problem. And I'm going to discuss the problem uh, and why it's so important. So let's say my loved one needs a kidney and I want to donate one of my kidneys to my loved one. And I find out that I'm not compatible. And somebody, let's say in New Jersey, is in the same situation that they're not compatible with their loved one. But we find out that I'm compatible with their loved one and they're compatible with my loved one. So we have this sort of two-way swap. I can donate my kidney to their loved one and they can donate their kidney to mine. And then everybody's happy, right? Everybody, the people that need kidneys get their kidneys and the transplants are successful. So this is a two-way swap. But these swaps could become very large, and that's the whole premise of the kidney exchange program, where it could be on a state level, it could be on a national level, and it could be more than a two-way swap. It could be three, four, five, six, seven-way swaps until you get to a very large combinatorial optimization problem. And when we take this problem and we feed this problem into SAS, because we have a classical optimization solver similar to Gurobi and Cplex. What happens is when we allow it to run, we get an optimal solution after 1 second. But not an optimal. I used the wrong word. A feasible solution after 1 second. It's not optimal, but it's only 3.3% optimal. So the question is, well, could we just use that solution, right? It met the constraints. It's feasible, but it's only 3.3% optimal, which means there is a good chance that if you donate the kidney, somebody will have a rejection to that kidney. So we allow the optimizer to run, and after 20 seconds, we get another solution that is feasible, and that's 96.6% optimal. But again, is that enough? Would you want to know that the kidney you're getting based on the optimization algorithm is 96.6%, compatible or optimal? Probably not. You're going to want to know that it's 100%. So we keep on letting this run, and after 180 seconds, we're at 99.4% optimal. And if we continue to let this run, it could go run for hours before we have to just manually stop it, and it doesn't get to 100% optimal. So we said, let's put this into a quantum solver. And in this case, we use D-Wave. And when we do this, we get a series of solutions after 14 seconds. And within 14 seconds, we get 101 solutions. Now, it's important to understand that out of those 101 solutions, 28 are feasible. But why are only 28 feasible? Because quantum is probabilistic and not deterministic, it's going to give you a probability distribution of every possible solution that it found. It's your job to determine if it's feasible or not and whether it's usable. And the other thing about quantum is that because it's probabilistic, you have no idea how optimal your solution is. How far away is from optimality, or how large is the optimality gap? So what we do is we take, in this case, we took the best objective that we got out of quantum. And again, we don't know how optimal it is, but we need to find out. So what we do in SAS is SAS allows you to what we call a warm start, and it allows you to start the solver at what we call a warm start, where we take a solution that we know is good and we feed it as a warm start, and we say, start your search from this spot. And we get now 100% optimal solution within 30 seconds. So if we just run it classically with no quantum at all, after 180 seconds, we still don't have an optimal solution. But if we combine in a hybrid approach, quantum and classical, with the classical part taking about 28.79 seconds and the quantum part taking 13.96 seconds, we get a valid solution or an optimal solution at 43 seconds about. Now, I mentioned that we had all these other feasible solutions. I think it was 28 feasible solutions in total. we don't need to throw those out, right? We could use sometimes choices are good to have. We could take all of those solutions and feed them in parallel to our VIA system, and it will run the optimization, the classical optimization, using each one of those as separate warm starts, and then come up with different solutions for each one of those. So in conceivably, you could turn around to a hospital or a kidney exchange, the governing body, and say, here are 28 optimal solutions that you could kind of thumb through as as environments change or as the relationships change or as your populations change. And here's my final example, and this one is called a reblend problem, and it's from a consumer packaged goods company. So you can think of we have product B that we need to blend with a bunch of ingredients to create a new product, product A, and uh, and that happens in a reblend tank. And when we reblend it, well, in this case, we're showing product A goes in and product B goes in. We get the mixture, and then we reblend to a new product. And we have certain constraints. In this project, we had certain constraints. Each stream could go into exactly one tank. So you have stream A, stream Y, and it goes into tank one. So stream X is not going to go into multiple tanks. It's only going into one. But multiple streams could go into the same tank. So stream Y will only go into one tank. And then each product can only be taken from one tank. Now, it doesn't seem like a big deal, but when you have a lot of different products, um, in this case, with up to 250 products and just six tanks, the number of possible combinations is 10 to the 114th combinations. So you really can't do this on a classical solver. So we did the exact same thing, and we ran it through um, the what do you call it, the quantum solver, and then fed it into the classical solver. And here's our objectives. Here are some variables. Here are the constraints. And when we ran this from the classical perspective, it took approximately 6 hours to almost become optimal, with the gap being 0.29%. In quantum, the entire problem took 2 minutes to run. But again, we don't know how far from optimal it was because it's probabilistic. We don't get that information. But when we combine them, when we feed that into our classical solver, in 12 minutes, we get a 100% optimal solution. So again, this is another example of quantum utility. So when we talk about quantum at SAS, our goal is to be a vision in the leader of applied quantum computing. And and I really want to spend a little bit of time on this. I call this the quantum pyramid of complexity. If you wanted to, if a user wanted to start using quantum today, they would have to decide, I want to use, superconducting qubits, I want to use trapped ions, I want to use neutral atoms, I want to use spin qubits, whatever it might be. And each one of those has their own version of Python that they sit on top of, or Julia, or Q Sharp if you're dealing with Microsoft. And you have to deal with all these different programming languages. On top of those programming languages, you have the SDKs. In IBM, you have Qiskit. In Quero or Neutral Atoms, you have Blockade. So you have all these different SDKs. In Google, you have Circ. You would have to learn how to program each one of these SDKs or APIs, and those sit on top of the different versions of Python and scikit-learn and things like that. And then on top of that, you have your quantum algorithms. So you have to start developing quantum algorithms, but not all quantum algorithms are good on the same type of hardware. So, for example, superconducting qubits have a very rigid layout of the QPU. So you have to design your quantum algorithm to kind of fit within the structure of the qubit layout. Otherwise, you're going to introduce a bunch of extra gates to move quantum states around. In trapped ions or neutral atoms, it's more all-to-all connectivity, so you don't have to work. But you see where I'm getting at. You have multiple languages, multiple SDKs, and then you have multiple algorithms that have to either be transpiled or compiled in different formats. What we want to do is we want to stick SAS on top of that. We want to hide all of this from our users so they don't have to worry about the programming language and the SDKs and all the different algorithms. We give them the opportunity to build algorithms if they want, but we're also going to provide them sort of industry standard or best of class algorithms that we've developed. And all of that will be accessible from within the SAS framework. So you can program all of this and access all this from SAS Data Step and Prox and SAS Studio, our interfaces, Enterprise Guide, Model Studio. So they don't have to know all the plumbing underneath. They just have to know how to use SAS. And that's where we just launched our SAS Quantum Lab recently. Well, it's a soft launch, but it'll be launched for the general public Q4. And yeah, that's my presentation.
Mm.
If anybody has any questions.